Today I'm going to discuss about some case studies on POSIT computing. So before that, I would like to give some introduction on POSIT computing, and and then move forward and some case studies, and then I'll finish off this video. So there are some problems in the computing industry. As you might know, these buzzwords AI, HPC, machine learning, or graphics computing. So these are heavy math computing applications. So these applications require high performance math computation, lower latency, and lesser data width, as well as high accurate results in HPC and in AI as well. So as a result, what's happening today is that most of the chips or soft IP cores are fabricated in a lower technology node, for example 7 nanometer or 3 nanometer or 10 nanometer and so forth. But the thing what happening is that instead of looking at the fundamental problems in the in the in the computation, specifically in the computer arithmetic, so most companies are fabricating the lower technology node. So we tend to look this problem as very fundamental to computer arithmetic design. So what we propose is that instead of um, fabricating a chip in a lower technology node, so you could think in a other way around. Why can't we change data width or increase the accuracy of a result, or with half the data width, and then the precision remains almost the same. So the solution to that is a POSIT number system. So POSIT number systems uh, is an alternative to floating point number system. So FP32 FP a floating point single precision, approximately 32-bit. Here you require a 16-bit. So if you want to compare with the double precision accuracy, POSIT require a 32-bit compared to floating point 64-bit. So there are a lot of advantages in POSIT number system. There are more accurate results, and the dynamic range is large. In other words, whenever you give input, now you can get you can put the range of the input range is large compared to floating point. And then so since the data width is reduced, so one may expect lower power consumption with respect to FPU counterpart. So the uh, POSIT arithmetic, or POSIT computing, you could say that they have a better closure results compared to any arithmetic computation, such as addition, multiplication, or reciprocal, exponential, inverse square, and so forth. As an example here, I have plotted pre-closure. So addition, so you could say that in addition you don't have any uh, closure. You don't have any not a number in opposites, and then the results are approximately on an average compared to real number, it's more than 70% accurate. In other words, they are inexact. And the percentage of exact result, which is exact, the correct results, are more than now I would say more than 17% compared to the float, only I would say 10 on an average 12%. And you can see on the top right corner, so posits are tapered precision, in the sense that you have more results, more accurate results. So the tapered precision corresponds to you have the extra 4 bits in a POSIT 32 gives you more accurate results. And on the left side, you can see that we have plotted the plotted result is for 8 bits, floating point 8 bits with the 5 exponent, and POSIT 8 bits with 0, 1, 2. So you can see on an average, POSIT yeah, 8 comma 1 gives you more accurate results than floating point 8 comma 5. and the fixed point. So around you can expect the accuracy up to around 2.5 uh, compared to POSIT, compared to floating point. 2.5 bits of accuracy. Usually in AI or machine learning, where the accuracy is required up to only 2 to 3 decimal digits. So you could say that with the floating with the POSIT bit, it can suffice this accuracy. So in AI or ML, so one need to compute a lot of neural networking computing. So you can see on the left side equation, it's a neural network equation. So computing or training a neural network equation. So in this case, the considered classes are ResNet 20. So this is used for image classification. KWS CNN1 and CNN2 are they are keyword spotting. So in order to determine classification, there are a lot of parameters are used, and then the multiply accumulate used in these classifications are around let's say on an average more than 5 million multiply accumulate. So compared to the float, the accuracy of POSIT is around on average 90 bits, 90 I would say on average 90.34 accurate results compared to float. Another application is I would say climate modeling. So in this case, uh, this is uh, uh, climate modeling of of a oceanic wave. So the simulation is taken for around 2000 kilometer to 2000 kilometer by 1000 kilometer in the area. So the partial differential equation on the left side, it can give it is is a um, um, there's an equation for um, shallow water modeling. So in this shallow water modeling, you can see zeta is a pressure and F is a horizontal wind force, and G into delta N is a pressure gradient force with a gravity, and D removes the energy on a large scale, bottom friction as well as small diffusion, and u into delta U is advection momentum, and this is considered more accurate shallow water modeling. So this is for the so in the oceanic, this is there are vigorous turbulence with meandering zonal current. So this simulation is plotted for around 25 days. As you can see on the right side, float 64 on the top, and POSIT 16,2, they are almost the same figure A and B. So in terms of tracer contraction, the simulation result. But the same thing, if you want, if you follow with the power float 16, the simulation goes out of it's not so accurate. So as you can see that POSIT 16,2 I would say outperforms float 64 in a double precision. So considering this, there is a root mean square plotted graph on the bottom left side. So you can see that in a POSIT, I would say POSIT 16,2 is outperforms float 64. So you could expect POSITs are performs much better than floats in a climate modeling. Another example is fluid dynamics. So in the fluid dynamics, we used people used Euler code propagation of shock wave in a air through L-shaped conduit. So with now the code is run with edge or height of 1 or 256 and approximately 1.3 trillion floating point operation over entire run. So as you can see that at t is equal to 0, now wave propagates in a chamber and then it diffracts around the corner and initiating a shedding of vortex from the corner. And in the figure B, you could see that in around t equal to 0.51, the initial shock wave reflects off the far wall and reflected shock wave propagates back upstream. So, and this encountering, vortex around t equal to 0.95. And then the reflected shock wave breaks up the vortices, shedding off the corner and reflects again off the near wall at several times. So what happens, eventually the flow moves down the channel with the propagating sequence of oblique shock waves and a great deal of, wave interactions. So you can see that, using this, the Euler 2D code. So the root mean square error, RMS error, so again the POSIT performs much better than a float, and the spikes you can see in the error plot is that this is a shock wave and the shock wave vortex impact. So another example, and I would say in a DSP in a FFT transform. So FFT are computed using this partial differential equation as shown in the slide here. So this is a 3D partial differential equation PDE. So using three steps. So the forward FFT, and then evolve by multiplying factor, and then inverse FFT. So and so in the forward FFT, the error computed in a float POSIT 32 inquire is that it's 5.85 10 raised to minus 2 in float. POSIT 32 is 1.60 10 raised to minus 2, and acquired 32 is 1.59 10 raised to minus 2. In the multiplying factor evolve, I would say POSIT 32 is around 1.15 10 raised to 1, and then 4.38 POSIT 32 4.38 10 raised to minus 1, and then 4.38 in 10 raised to minus 1 in acquire as well. So in the final step, and you can see that I would say in inverse FFT. So it's around you could say 8.30 10 raised to 3 in float, 3.19 around 3.1 and 10 raised to 2, and 3.18 in acquire 32. So as you can see in the plot is that again POSIT 32 outperforms floating point. So you could expect the digits around 1.5 digits more accurate than floating point. So people usually say that, okay, that's great. So, but we don't have a need now. So we have floating point unit in our code. So the customer usually don't ask us in a unit. So I would say it's not about the need. So it's about how much you're going to lose, in terms of customer trust, or how you compete. So as you know that in electronic gadgets, mobile phone or a laptop, every couple of months you see a new machine, but the new machine is more expensive than compared to the previous one. So that is because chips are fabricating in higher the lower technology node. So since the fabrication cost is high, the of course the gadget cost would be higher. So, but I would say that most companies are not thinking in terms of customers' pocket. They are not, in other words, they are not taking care of customers' money. So, if you could clearly communicate, how you are taking care of their pocket, so that will be, customer will trust you. In other words, let's say, so if you fabricate a chip in a instead of fabricating in a lower technology node, the 3 nanometer, 7 nanometer, you can keep, let's say, 60 nanometer or 18 nanometer or any other than state of the art. But in the meantime, you reduce the fabrication cost, operating cost as well. So because these POSIT type cores, since there is a half the data width of compared to floating point, so there is a, it's not the silicon is not going to be much denser, so resulting, you have less transistor in a die, and then the power consumption is a half compared to the previous one. And moreover, the you're not going to fabricate a chip in state of the art. Maybe you can do it in 18 nanometer or 16 nanometer and so forth. So if you communicate that, let's say, let's say, a smartphone is costing around $1,000 in this month, and then you come up with a smartphone with a better feature, or a laptop with a better feature with a, let's say, a cost of half, $500. And then you can communicate clear to customers that how you reduced the cost, how you solve the problem, and how you taken care of their money. So eventually gain more trust from the customers instead of charging more. So what happens, the customers will be more inclined towards your brand, so they are emotionally attached towards your brand. So you ultimately you're going to be have more profits. So since they are emotionally attached towards to your brand, so you don't need that much marketing budget. So so the word of marketing will suffice in this one. And you don't need to compete with other products. If you taken care if you I would say clearly taken care of customers pocket, you don't need to cut through competition. In other words, you need to take care of your customers like a baby. So by doing so, no, you don't need to compete with the rest of the other companies. So no, the bottom line is that POSIT course will help you to uh, reduce the cost of the chip. And then you could say you don't need much marketing budget. So the whole the 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 chip or the performance, or no, it will tell to the customer that how you are taking care of their needs. So yeah, that's it. If you have any questions, please do get back to me on the social media, or you can visit us, and then you can contact us directly. Thank you.